Welcome to chemistry class. We are in session 6 of the chapter Chemical Kinetics. In this session, let us understand the various methods for the determination of the rate law, rate constant and the order of reaction. And all these can be calculated almost by the same means. First, let us understand the graphical method for the determination of the rate law. So this method is used when there is only one reactant and it involves the following steps. The first one is the concentrations of the various reactants are measured by using some suitable methods. First we need to measure the concentration of the reactants. Then we need to plot a graph between the concentration and time. So what is the second step? We need to plot a graph between the concentration and time. Then the instantaneous rates of the reaction at different times are calculated by finding out the slopes of the tangents corresponding to different times. Already we had learnt in the first session how to calculate the instantaneous rate by finding out the slope of the tangent corresponding to different time. Then the rate of the reaction which is calculated, that is to be plotted against the concentration or the square of the concentration, that is R square, and so on. Suppose if the rate of the reaction remains constant in this rate concentration graph, it means that rate is independent of the concentration of the reactant. So here in this particular graph, the rate is constant. So even though the concentration is changing, the rate remains constant. So this indicates that given reaction is of zero order. So for this one, rate is equal to K into R power 0, means which is equal to K itself. And if a straight line is obtained in the rate versus concentration graph, it means the rate is directly proportional to concentration of the reactant. Means rate is equal to K into concentration of R. Therefore, this particular reaction is of first order. And if a straight line is obtained in the rate versus square of the concentration graph, it means that rate is equal to K into R square. And therefore, we can say that this is of the second order reaction. Similarly, if we get a straight line in the rate versus concentration cube graph, it means that rate is equal to K into R cube. So and the order of the reaction is therefore 3. This is third order reaction. So in general, if we get a straight line by plotting the graph of rate versus concentration to the power of n, where n is equal to 1, 2, 3, etc., then we can say that rate is equal to K into R power n. So the order of this particular reaction becomes equal to n. So whatever is this n value, and if you are getting the rate versus concentration to the power of n graph as a straight line, then we can say that order of that reaction is equal to n. So that is how graphically we can find out the rate law as well as even the order of the reaction. Let's discuss this sample problem. So here is the experimental data for the decomposition of nitrogen pentoxide according to this equation. And the data given here is the time in seconds, this one, and the concentration of N2O5 in mole per liter, where we need to multiply the given values with 10 power 2. These are the things which we need to solve here. The first one is we need to plot a graph between concentration of N2O5 and T. So based on the given values in the tabular form, when we plot a graph, it becomes like this. So this is the answer for the first one. Then second one, we need to find out the half-life period for the reaction. So how we will calculate the half-life period for this particular reaction? Here the initial concentration of N2O5, this is given as 1.63 into 10 power minus 2 molar. And what will be the value of half of this concentration? and that is nothing but equal to 0.815 into 10 power minus 2 molar. So when we take the value corresponding to that 0.81 into 10 power minus 2 molar, it comes like this. So this is 0.6, this is 0.7, this is 0.8, 0.9 and this is 1.0. So this is the time and this is the half-life, and this value it will be somewhere around 1400 and 1500, and when we calculate it exactly based on the scale, we will be getting around 1440 seconds. So at the concentration of 0.8 we can find out the time, and we will be getting the half-life for that particular reaction. And third one, we need to draw a graph between log of N2O5 and the time t, and it is like this. This is the concentration and this is the time, and here the concentration is exactly log of N2O5. As it is negative value, it is in this particular way. So we are getting a straight line. Then we need to find out the rate law as well as the rate constant. So for getting the rate law, as the plot of log N2O5 versus time, it is a straight line, hence this is of the first order reaction, because here we get the expression like this: rate is equal to K into concentration of N2O5. Then how we will calculate the slope of this line? For this one, slope is equal to minus K upon 2.303. So it is y2 minus y1 by x2 minus x1. It is minus 2.46 minus of minus 1.79 divided by 3200 minus 0, and this becomes minus 0.67 by 3200, that is K by 2.303. This is equal to 0.67 by 3200, and on solving this we will be getting K as equal to 4.82 into 10 power minus 4 mole later inverse. Then again we need to find out the half-life period from K, and we need to compare with this particular value. And we know the formula half-life is equal to 0.693 by K. So which is equal to 0.693 by 4.82 into 10 power minus 4. And on solving this, we will be getting it as 1438 seconds. What was that value which we got based on the graph? It is somewhere around 1440 seconds. And the value which we got from the rate constant K, that is equal to 1438 seconds. So it is almost the same value. That is how we can use this graphical method for finding out the half-life, order of the reaction, rate constant, etc.